Okay, good morning. We are going to have today's lecture in longitudinal dynamics of our vehicle for a passenger car. What is braking performance study, right? So when I say braking performance of motor vehicles, it is undoubtedly one of the important characteristics that affect vehicle safety. So we know braking immediately in here, it connects to vehicle safety is concerned. And during emergency of braking, see the vehicle can go into an unstable state. So that's what we are going to look at it now in today's class. What is that it decides the braking performance to avoid this kind of unstable state? It can safely brake without any problems to the other vehicles on the road. When we say other vehicles on the road, traffic safety is very important. So when you are driving on highways and you have to apply your brakes suddenly, then because of your vehicle go in unstable state or disturbed mode, and that should not affect the other vehicles. And in case it happens unavoidable, see there is series of accidents that happens. So the traffic safety would be question mark if an individual vehicle is not having an appropriate brake system that would ensure all the time the vehicle safety, right? So that is what made many of the countries to come out with many standards regarding to brake system in a vehicle. And that is today in a foolproof condition that every vehicle has got a very good modern control strategies that the braking of vehicle would result in a safe braking and avoid unstable state of a vehicle, right? So when you say this braking performance, we are having two things in our mind. One is the criteria for evaluation of the braking capability of the vehicle that we should understand. Another one is what are the different approaches that are gone into improving the braking performance of the vehicle, right? So I'm going to teach you today looking at the dynamic equilibrium of your vehicle during braking and looking at your tire wheel assembly or an individual wheel during braking. How does it affected by the forces and moments, and then we will develop the condition for maximum braking effort that should be developed at both axle wheels simultaneously, so that you would not have a problem of one axle wheels are braking before the other axle. So all the wheels, that means the front and rear axle wheels, or in case of a two axle vehicle, should brake simultaneously, and that would happen when you have the maximum braking effort is realized at the tire road interaction simultaneously. So we are going to look at what is the condition for having such kind of maximum brake force distribution called an ideal braking force distribution in today's class, is what is the objective of the lecture, right? So let me just share my screen and go ahead with our lecture. So hope you are able to see. This is what in the last class we looked at when we are looking at the power required for the vehicle to overcome the resistance, and then we were able to understand the importance of the manual transmission system. And we also have learned the manual transmission system for a vehicle acceleration performance is concerned. You require to look at first the maximum achievable speed of the vehicle to be decided, and then you should look at for the intermediate gears the condition that the engine should operate in the same speed range irrespective of the gear is in operation. Is in operation means the vehicle is redundant with any of the gear, no matter, but the engine operating speed should be in the same range, and that is what is decided by geometric progression with this ratios called kg. So with this basis, we were able to understand how the gears are designed in a gearbox of manual transmission system. Of course, for the lowest gear, the condition is to look at how good your vehicle is able to grade when you go up the slope of 33% at the lower speeds, and at the same the higher speeds of a gentle slope of 0.3% at say 90 to 100 kilometers per hour, if your vehicle is able to go, then your vehicle is of good accelerating performing vehicle. So these are the bases that we have seen. So the advantage of having your IC engine along with your transmission system is what is that we realize that could provide an ideal power requirement. Though we are very much knowing that an individual IC engine, if you look at, without it's employed on a vehicular application, their braking, their power or torque characteristics is appearing not viable, but it has been exploited and can be employable in your vehicle along with the suitable transmission system is what we have learned in the last class, right? Now in today's class, as we have started our class, we are going to look at what is braking performance of our vehicle. So let me just start today's class. Just give me a minute. Just have to arrange this. Yeah, so this is lecture number 39. And today's date is 29/11/2021, and we are going to study braking performance of two-axle vehicle. So when you say two-axle vehicle, it can accommodate not only a passenger car, also it can accommodate a light truck, a small van, and so on. So two-axle vehicle braking performance is what we are going to look at it. So the moment you say this braking performance, what is that comes in our mind is vehicle safety. Along with that, traffic safety. Along with that, traffic safety. And this traffic safety led many standards, right? Safety standards for braking system are being enforced. So many safety standards for brake system came into effect, and importantly, every vehicle nowadays is enforced to have ABS, called anti-lock brake system. So today's lecture, by understanding how can we, what is the condition for having maximum braking effort at both the axle tire wheels, is what is the basis for looking at the requirement of operational characteristic of ABS system, right? So let's look at in today's class two important free body diagram. One is a vehicle free body diagram, another one is individual wheel free body diagram. So let's look at, like in the last class we derived for acceleration of the vehicle. Let's look at now for deceleration. So let's consider a gentle slope. On this, I have my vehicle. This is two-axle vehicle, a passenger car I consider here. And the CG location somewhere here. So the total weight of your vehicle would be resolved into two components, one normal to the road surface another one is along the slope. So in this case, so this is your W cos theta s, and this is W sine theta s. And then the two normals that are acting here would balance this W cos theta term. So here I have WF normal load, the front axis, WR the rear axis. So now the vehicle is what it's for braking. This is braking scenario of our vehicle. So let me just take this down. And here what we are studying here is braking. So it is a free body diagram or dynamic equilibrium of a vehicle, of a car during braking. This is what we are looking at it. So when it is braking, what is that is happening? There is a brake force that are acting on these wheels. So they would be acting in opposite direction. They would be acting in opposite direction. So if these wheels are rolling up in a clockwise sense, then the brake force would be opposing that. So I would have my braking force, say this is FB, F and FBR. And along with that, of course, we had already looked at rolling resistance force RRF and RRR. So these are the forces that are acting when I apply the braking, the tire rod interaction, and the vehicle in a forward direction when it goes with the velocity u, and this velocity now has been decelerating because of braking of the vehicle through the brake system in our vehicle. I would have here now my deceleration. So the load transfer would be what? The load from the rear would be transferred to the front, and your deceleration, so the direction of deceleration is in this direction. So I would have an inertial force in the forward direction. That's called a D'Alembert's force for an equilibrium, and that would be W A by G, where here A refer to deceleration. Vehicle deceleration. And of course, along with that, if my vehicle goes in the slope with the high speeds, then I can't neglect my aerodynamic resistance. And I also consider, say, drawbar resistance. Then these two would come, and this would be acting at a HA distance, and this is at HT distance. And of course, this CG location from ground is at a height small h. So this is what is my free body diagram when the vehicle is braking, and the dynamic equilibrium diagram. So the same if I look at my individual tire. So now if this is the direction of angular velocity, when I apply braking, the braking torque should be in this direction. Applied braking torque, let me call T subscript B, is in opposite direction. So my vehicle's moving in this direction with the velocity u in forward direction, and that's because of this omega angular velocity of this. When I apply braking torque to my vehicle through the brake system, then what will happen? I would have my omega reduces. That's because of an angular deceleration, omega dot or alpha. So this I can call this as alpha. So this alpha would ensure there would be a necessary couple moment called inertia couple I times alpha. I times alpha. I times alpha. This is angular deceleration. So what is alpha? Angular angular deceleration, and this I times alpha angular deceleration is what is the inertial couple that is for the dynamic equilibrium ensured. So now along with that, what additionally that I have of course my load here, and that's why I have it here, my F is that, and I would also have now the braking force. When I apply the braking torque here, the contact between the tire and the wheel, I would have a braking force developed. So that is, if this is rotating in this sense, my braking force to develop in the opposite sense, right? Direction should be carefully taken. So this is braking force direction, FB. And this FB is limited by mu p times W or this FZ, mu p times W or FZ. So that is what is the limiting value, maximum value of FB. So if my vehicle is translating to the right and my FB is opposing the translation of my vehicle wheel center, like that, the vehicle wheel center translate is because of rolling motion of my vehicle wheel, right? And when I apply driving or braking torque, that reduces my omega, that represent angular deceleration. And when an angular deceleration acting like this in this direction, then I will have my D'Alembert's braking D'Alembert's couple that act here for dynamic equilibrium, right? Yeah, so now this would result in this equation. So if I have my equation taking moment about point as the center of my wheel, if I take in this case equating to 0, so I would have now FBR into R. So this is rolling radius R. So that's I'm going to take counterclockwise moment positive if I consider. Then it is minus FB into R by this, and I have my minus I alpha angular couple, that's again clockwise, and this plus TB counterclockwise, and these are the three couples that is equal to 0. So I would have now these three moments equating to 0 results in what is my braking force FB. If I take it on the other side, I would have that's TB minus I alpha by R. So FB is equal to TB minus I alpha by R is what is defined, what is giving me what is the braking force magnitude that comes here. So this braking force, when it reaches to the maximum value FB max, that is the point of approaching mu p to mu s, that is going to be a skidding point, that is going to refer to a locking point. But now this is not locking scenario. This free body diagram is deceleration, angular deceleration, that doesn't resulted into locking of the wheel. So when you have locking of the wheel, this FB become FB max, and that would be equal to mu s times FZ instead of mu p times FZ. So that's all something that we should remember. So the wheels are not expected to lock all of a sudden. The wheels are always to gradually lock and stop, gradually stop, not locking, gradually stop. So that is what is expected, and that can be achieved through an ABS system. We will see that in the next class. But today's this free body diagram and this discussion would give you an idea of what are the requirement characteristic of your ABS system that should be met. Right, so this is the explanation of how this FB developed, what are the various forces and couple moments acting in this wheel, in a single wheel that you have seen, and that is what is responsible for generation of FBF and FBR. So FBF and FBR, and this would come how? It would come the moment TB is applied and its equilibrium, all what I explained here is resulting into this. Okay, so other than this major force for braking is developed because of brake system, you also have in a vehicle a rolling resistance force and your other resistances that are grade resistant W sine theta S and your aerodynamic resistance, your drawbar pull resistance, and of course your inertial force acting in this direction, right? So this is not acting as resistant, but this also to be accounted. So these are the forces. So how do I get now the condition of having the maximum values of FBF and FBR here? So that's what we have already looked at. So FBF maximum value would be MEP times WF, and FBR maximum value is limited by MEP times WR. So the maximum values limited by this MEP times WF. So I require now the normal loads at the front and the rear axle. So how can I get that from this free body diagram? I can get that simply. So let's call this point A, the tire road interaction center, and this point is B. Now let's go and take moment about point B to get WF and point A to get the moment to get WR. So let's have that. And before that, let me write the force balance equation for getting what is the resultant force in X direction. So that would be, let me consider now here the direction up and this positive like that. If I consider, then I would have my resultant Fx equals 0, considering this convention here of positive, that would be equal to this. So when I write that, I would have FBF minus FBR, they are down, minus RRF minus RRR, rolling resistance force, and other forces are minus RA minus W sine theta S minus RD plus WA by G, at all equal to 0. So I would be able to have my resultant force is given by Newton's equation. If I say that's equal to WA by G, and that would be equal to the remaining all terms taken on the other side. So these two together I will call as FB, braking force in both axle sum, and these two together I will call rolling resistance force, RR, and this RA plus RD plus W sine theta S is all what is my resultant force here. And this resultant force, I wanted to write the force at the tire road interaction, that is the required forces for braking your vehicle, that is FB plus R rolling resistance, and that would be equal to now rest all if I bring in here WA by G minus RA minus RD minus W sine theta S. W sine theta S. Right, so let's call this equation as 1. So these are the braking force. So here you could see this rolling resistance is always aiding braking. So that is resistance for accelerating your vehicle, but the direction would not change. Always it would be opposing the motion of your vehicle. So the rolling resistance always aid in braking. That's why it's get added with the braking force, total braking force. So now this is our equation 1 first. And then now let us look at what is my WF and WR. So for that, let us take a moment about point B, the rear axle getting to 0, considering counterclockwise moment positive, I would be able to derive the expression. So first let's start with the WF into L, and one by one forces let us account, and let me write down, you can just to cross check. You can also parallelly do WF into L wheelbase is what is the moment which I am interested in. This equation is WF. L is wheelbase. So this is counterclockwise moment. Similarly, plus W sine theta S is grade resistance or weight component along the slope into H is what is CG location from the ground. So this is again counterclockwise moment minus uh, now weight component W cos theta S into L2, then aerodynamic resistance into HA, then drawbar resistance into HD, then the couple due to moment due to inertia force, D'Alembert's force is clockwise, so that's W A by G into H. So this is all equal to 0. This is what is that moment equation applied. So 1, 2, 3, 4, 5, 6 terms are there. 1, 2, 3, 4, 5, 6 terms are participating in this equation. Rolling resistant force will not come as it is on the ground itself, right? And FB will not come as it is also on the ground itself. So these are the forces elevated from the ground, and point B is the rear axle tire rod interaction contact path center. So I take their moment, I get this equation, and this would nicely result into WF would be equal to, let me look at here. So at a small angle, if theta S is small, cos theta S can be considered as 1. If I consider that, and this term is going to be WL2, and then it goes on that side and divided by L, this is going to be WL2 by L plus, and I also consider this H is equal to HA is equal to HD, like that. Then I would have in this drawbar resistance I can neglect as in my free body diagram. I don't tow any of the vehicles, so I don't consider this moment, and the rest of this 5 terms would result into this. So since I have these heights of these 3 other resistances are at the same level by H, then H by L into, I would have inside the bracket. So this goes on that side, so this is positive term, so WA by G. And here RA goes on that side, that's negative, so RA minus, this is also going on that side, so W sine theta S. So this is what is that I have my second equation, and that gives me what is WF. And you can see this WL2 by L is what is static component, and this is what is the dynamic component. And you see now this is plus sign, unlike what we have looked at during acceleration. Now this is plus sign. So you get this term added to this. So that shows that load transfer, longitudinal load transfer takes place during braking. And this is that addition of your normal load along with that vehicle when it is on a level ground with a constant speed when you look at it, right, in a straight motion. So similarly, you can get now what is WR. That's going to be obtained by taking moment about point A, looking at the free body diagram of the entire vehicle. I can get that. Then it is going to be WL1 by L, and instead of plus I'll have minus, and H by L, and will have the same terms inside. This is my third equation. This is my third equation. And it is going up the slope. Suppose you are asked in the exam, or you have to work out when you are coming down the slope and you are applying brake system, what would be the change in this equation. You have to see this term would change into plus and this term change into plus, right? That you have to remember. And now see, from equation 1, I can replace this equation 1, whatever that I have. The moment I neglect here this, I can also neglect this term here. Neglecting that, there is no towing, there is no drop or pull. Then I have these three terms appearing inside this bracket of equation 2 and 3 can be replaced by FB and RR. So my equation 2 and 3 now become, my equation 2 is now become WF is equal to WL2 by L plus H by L into FB plus, RR is given as rolling resistance coefficient times the load W. That's my equation 4. And WR is going to be WL1 by L minus H by L, then bracket FB plus FRW. That's my equation 5. Then we know that FB max is limited by mu times W. We know FB braking force maximum value that can be developed is limited by road adhesion coefficient mu P times W. When wheels are not locked, then this braking force maximum value is decided by the brake system performance. That means what would be the cylinder pressure, brake pressure in the cylinder, and that is being supplied to the braking wheels. So the design of brake system would decide before the value of mu P times W reaches. But if your braking force value from the free body diagram here reaches to the value of mu P times W, then it has been limited by your road adhesion coefficient. So your brake system can distribute the braking force in front axle and rear axle such that it can go just to this value, but not to the value or beyond the value, because when it is reaching this, that is the point of impending that vehicle wheel locking would take place. So just to prevent wheel locking and wheels to decelerate gradually, then gradually at the same time, at the shortest distance to wheel to go, I should reach my FB developed at the wheels closer to this value, not to that value and beyond that. So that's what would be taken care by your ABS system. Right. So if you are having that understood, then we would be able to now write the expression for your maximum braking forces. So the maximum braking force now, FB, F in the front axle maximum, is now given by mu P times WF. So let me substitute this equation 4 in this. So that's going to be mu P times W within bracket. I would have, see now, what am I doing is I'm taking this term, this fourth equation you look at, I'm taking W out. Here also W is there, right? I'm replacing this by mu P times W, right? So if I do that, I would take this out, and I will have inside, this is going to be L2 plus H into mu P plus FR. So this is my expression divided by, of course, L. This L will be there. So here L is there, here L is there. So when I substitute mu P times W here, and then I take from this W by L out, mu P W by L out, then I'll have my expression goes like this. So this is equation number 6. And similarly, I'll have FBR max be mu P times WR. So substituting equation 5 into this, so I will have mu P times W by L if I get L1 minus H into MEP plus FR. That's my equation 7. That's my equation 7. So what is to be noted? So it should be noted here that when the braking force reaches the maximum values, this braking force reaches the maximum value given by this equation, the tires are at the point of sliding. So if it is reaching to this maximum value, the tire, instead of rolling and then decelerating, it would be sliding. It's a point of sliding point it comes. Any further increase in the braking force from this value would cause the tires to lock up. So the locking is happening slightly more than this value would make that wheels to lock, and that means there is no rolling action, it is only sliding action, and that should not happen in your vehicle. So all the wheels of front and rear axle go simultaneously and lock, then it would be nice. So now the challenge is what? So I have my road surface, and the road surface is having this MEP value constant, then it is okay, fine. If I have my vehicle ridden, and on right side I have road surface, dry surface, on the left side I have, suppose, some grease is there on the road surface, and the MEP value is different there, then difference in MEP on right side to side, right side one value, left side one value, then again the distribution of braking force is not easier, like from this expression what we express. So that is what is that you require an anti-lock brake system. So there will be a wheel speed sensor. So that would look at the what's happening and brake system is applied, so that will have the threshold value of the speed permitted, and accordingly there will be signal taken to a control unit, and then it would go to the cylinder, brake cylinder, where the brake pressure can be modulated and so on. So we will see that in detail, the characteristic of ABS requirement and what are the different types of ABS system in a two-axle vehicle in the next class. But in this today's class, we have derived this expression that can be developed or supported by the tire rod interaction when the brake system supplies the driving torque to the wheels, and limited by the road adhesion coefficient. So here is what you have to have to define ideal braking force distribution. Ideal braking force distribution. So ideal braking force distribution is the total brake force that comes from the brake system. How much is to be provided on the front axle, how much is to provide on the rear axle, is what is the braking force distribution that we are talking on. And that ideal braking force distribution would be achieved if the distribution of braking force is same as that of the ratios of normal loads that are acting on the wheels in the front and rear axle. So if I say that, I can put that in this fashion. So KBF by KBR, where KBF and KBR refer to the proportion of the total braking force in the front and the rear axle respectively. And that ratio should be same as that of FB F max by FBR max. So if I put that, substituting equation 6 and 7 here, I will have MEP times W by L into L2 plus H into MEP times MEP plus FR by MEP times W by L into L1 minus H into MEP plus FR. So this is what is that ratio that I get. Let's look at that equation number 8. So in this WW go off, MEP this goes off, but this L has to be taken inside. So it is L2 by L, H by L, and this is L1 by L minus H by L, and so on. So to understand this, let me consider a light track. A light track. Let's consider a light track. And the load distribution of the light track is 68% of the load, 68% of total load is on rear axle, right? A truck with 68% of total load on the rear axle during braking. That means what? During braking, sorry, during static load condition, not braking, because that we do not know what is happening. So we know that when the vehicle goes in a straight road, light track, and with the constant speed, then you see the 68% of the load is on the rear axle. That is static load. Static load means it's not representing vehicle to be stationary. The vehicle can go in straight line motion with the constant speed. The Newton's first law, right? It would continue with the same speed. Then it is again a static condition. At that time, the load is 68% of the total load on the rear axle. So what does that means? You know, WR would be in such situation from the free body diagram, as there is no acceleration or deceleration. So you would have that is given by WL1 by L. From the simple free body diagram, one can get it. So it is 68% of that means this is equal to 0.68. So that tells you the ratio L1 by L is what is 0.68. So if that is so, remaining total load of 32% would be on the front axle. So WF will be WL2 by L is what is going to be 0.32. So that says what is L2 by L, that's going to be 0.32. So having this in hand, also additionally the data here given is H by L, the CG location of your truck from the ground to that of wheelbase ratio is 0.18. And your rolling resistance coefficient given in this case is 0.01. And the road adhesion coefficient, so we consider the dry road surface and MEE on both sides of the wheels are the same, is 0.85. If you are given these values, then you would be able to substitute them in this equation number 8 and look at what would be the requirement of braking force distribution. So KBF by KBR would be equal to 0.32. Because you look at what is in numerator, it is L2 by L. L2 by L is 0.32. L1 by L is 0.68. So substituting that, I would have 0.18, that's H by L. And inside I have μp, that's 0.85. And my rolling resistance coefficient 0.01. So that is the numerator. And in denominator, 0.68 minus 0.18 into 0.85 plus 0.01. So this would give me value 0.47 by 53. So what does this refer to? So it refers to 47% of total braking force must be placed in the front axle. So this tells that 47% of total braking force in the front axle and 53% on the rear axle. If this is happening, that would reach to, so for axle, for ideal braking force distribution, for ideal braking force distribution, ideal braking force distribution, and that would ensure the maximum braking potential capability of the vehicle, right? So if this distribution is not given to the vehicle, what would happen? That's the question. So if this is that exact proportion, I have my braking force distribution in the front and the rear axle, right? So see, this equation accounts the dynamic load transfer also here. This first part of this, the 0.32 and 0.68 only is static condition, but during braking, whatever the other forces are there, inertia forces all accounted here. So if I have my data given, and then if I substitute, I know what would be the recommended braking force distribution, and that would be an ideal braking force distribution. Why is it called ideal braking force distribution? Is because all the wheels would stop simultaneously or lock simultaneously and stop. So when I apply this brake, and this is the distribution in the truck ensured for the emergency braking, all wheels lock simultaneously. That means I would be able to achieve my vehicle stopping distance in a straight line with the shortest distance possible, right? So that is what is that you should understand from this. So now the question on the other hand is, in case if I do not meet this, what would happen? In case if I do not meet this, what would happen? If my braking force distribution is more than that of 53% in the rear, and front will be lesser than 47%, what is the condition? Front wheel tire wheels will be rotating and rear wheel tires would be locking. So when the rear wheels are locked before the front wheels in my two-axle vehicle, and that is not preferred situation, and then what will happen? The wheels which are locked at the rear axle cannot support or resist the smallest side force that can be induced due to wind gust, or maybe the road camber, or maybe by the centrifugal force itself. So it cannot support the necessary lateral force requirement, and that would be drifting out, and then the entire vehicle would have a yaw motion with respect to a yaw center in the front axle. So let me just put this picture really, you would understand, right? So I have my vehicle. Another 5 minutes, we'll stop the class. I have my vehicle here. So this is that curved path. Here the vehicle comes straight. And this is a schematic representation of my vehicle. This is the rear wheel. This is my front wheel. And this is CG location. I see this vehicle from the top. So this is point O, front axle center, yaw center that I call. So now what does that happen? When I apply this, I require to apply braking on this. If my braking force is such that rear wheels lock before the front wheel, right? Case 1. Rear wheels lock before front axle wheels. Then what would happen? You see that there would be an inertia force. Let's look at this scenario would change. My vehicle would have some yaw motion instead of going in straight. That's all because of there is no sufficient force that can prevent this skidding. So my vehicle would drift in this side, and that would make the force, whatever the braking force that comes here, resultant braking force in the vehicle at this point O, FB. And you see this inertia force would act in this direction. That is, say, W A by G. So you can see they are not collinear. So when it goes straight, when all the wheels are locking together, this FB will be equal to this, and then no, it would be just stopping. But when it is not so, the FB at the CG location, see this is equivalent, that's all taken and collinear, like that you can consider, and that would not be no more collinear, and this would generate here a yaw moment, and that yaw moment is because of these wheels are locked and they are drifting out, so there will be a rotation initiated. Then this your inertia, your brake effect force, braking force, which is equal to WA by G, that would create a moment, yaw moment into the disturbance. So this is coming from here, wind gust is wind gust. is coming from this direction, that makes this is happening. The smaller disturbance in a vehicle from the side would precipitate this event. And here you see this couple is going to be this distance. So if I extend this distance initially collinear, so this distance is 0, but then this distance increases, and that would become maximum at 90-degree turn, and then again it would start decreasing. But by the time you cannot realize, in no time you would see that vehicle reversed in its rotation. So this is your rear and this is your front, and it would be completely rotated. So on the other hand, case 2, front wheels lock before rear axle wheels. What would happen at that time? The yaw center would get shifted onto the rear axle, and here you do not have sufficient force to resist its motion. So the wind gust is acting, this would be drifting on this side, and you would have a yaw moment in an opposite direction, that is self-correcting, self-aligning. So the driver would lose the control of the effective steering control would be lost, but he can exercise controlling and bring the vehicle onto the course, and that is also get assisted with the help of the moment. So at that scenario, what would happen to this force? It will be like this. Your yaw center would be here. If you look at, so here the vehicle comes straight. This is your rear axle. The smaller one is your front axle. And now this would be drifting here because these wheels are locked, but the rear wheels are rotating. So this is your yaw center O, and you would have a total braking force acting in this, and you would have the scenario changes like this. So the distance here, you'll have your FB, and this is your WA by G. So now you look at this direction. So this is going to be, this couple is going to be bringing in. So when this goes like that, this is going to be bringing in your couple, right? So this would be on the side. I'm sorry, this diagram. This diagram. This is my FB. So it will be self-correcting. So this is drifting, and this would be self-correcting. The couple would be in this. So instead of going away from the course, so here the disturbance wind, and the vehicle rear wheels are rotating, front wheels are locked. This would be going out. So the steering requirement should be counter steer, so that it will be going straight, and that get assisted with this. So this is self-correcting couple. Whereas in this case of rear wheel locks before this, it is not self-correcting. It is a couple that induce the vehicle to turn into the disturbance, and it's kind of oversteer tendency that we have looked at, and the stability is a question mark. So in the case 1, vehicle is unstable. The case 1, vehicle enter to unstable state. Whereas in the case 2, vehicle lose its directional control only. But the directional control can be carried out by an alert by the driver, and he could have a steering control. The directional control lost can be corrected by an appropriate steering input by the driver. Whereas here, driver cannot do any more exercising of steering, and the total control is lost, and then it is an unstable state. So most of the legislative act that comes from different countries are, though expecting that vehicle wheel locking should be simultaneous by an ideal braking force distribution to be ensured, In case it is unavoidable, the situation that the vehicle can be permitted for front wheel lock instead of rear wheel lock. And we will just look at in the next class. We will see that there are some condition. How can you ensure looking at the given parameter of the vehicle and are the wheels are locking simultaneously or which wheel locks first, and to question on these two, whether the vehicle for the given data, road data and vehicle data, is vehicle enter the unstable state or directional loss state. How can you identify through equation? We will see. That means some quantitative measure by equation we'll see in the next class, and also get into understanding working principle of anti-lock brake system. So that's what is in the next class. On this Wednesday I'm going to teach. At this moment I will stop today's class. If you have any doubts you can ask. Otherwise I will end the lecture now.